So let's get started again with CH5010 chemical reactor theory. So we have finished module 7, now we are at module 8. Okay, module 8 we will go back to what we started off in module 1. We'll talk about reactors and we are going to talk about ideal reactors. Ideal reactors, of course, you know, that is for our case, the ideal reactors that we talk about are batch reactors, CSTRs, plug flow reactors, right? Uh, Overall balance equations, those are the Bird-Stewart Lightfoot type or transport phenomena type models that's covered in chapter 7 from and Bischoff. This is what we covered at the beginning of at the end of module 1 and beginning of module 2 in this course. Okay. Special case of batch reactor is there in chapter 8, plug flow reactor in chapter 9, CSTR in chapter 10. Okay. As far as this course is concerned, we will consider all of these reactors in this particular module. Okay. Essentially, when we considered this as an undergraduate course, we spent a lot of time distinguishing PFR, batch reactors, CSTR and all that. Here we are going to look at basically CSTR as a special case of well mixed reactors, batch reactors as a special case of well mixed reactors. And PFR, we started off this course with giving an analogy of if you put a batch reactor on a conveyor belt, what you see variation in space is essentially the equivalent of how the things are going to change in that batch reactor. Of course, that's a simplified situation. That actual situation is valid if you have, let's say, a liquid phase system and the reactor diameter is constant, which basically means the size of each CSTR as it goes through, or sorry, size of each batch reactor as it goes through on the conveyor belt, that size of that reactor, as long as that doesn't change, you have whatever happens dc by dt in batch reactor happens is dc by d tau in a plug flow reactor. Okay, we spent a good half a lecture right in the first week, end of the first week or the beginning of the second week of this course. Okay, so for all those reasons, all of these we are going to cover them, under a unified framework, that if the reactor is an ideal reactor, then how we are going to do the analysis. Okay, so which basically means we are not going to cover each and everything. I mean, in these chapters, we are going to pick and choose what we are going to cover. So we are directly going to look into energy balance equations. Non-isothermal, isothermal system is going to be a special case of non-isothermal system. You have already solved, semi-batch reactor problem right in your assignment 1. So you have already done that, and we are going to build on the things that you would know. So yeah, okay. So over the next several slides, I'm just going to recap what we have covered, and please go back and look into module 1 for the details. As I said, the ideal reactors, batch reactors, CSTRs and plug flow reactor. Batch reactor, we look at unsteady condition. There's no inlet, there's no outlet. Semi-batch reactor, there might be only one inlet or only one outlet, or there might only be inlets or there might only be outlets. So that's what we consider in semi-batch reactor. Continuous stirred tank reactors, again, in your undergraduate CSTRs, you have always considered steady state situation, and probably 2 days in the entire semester you might have done transient CSTRs. Okay, as far as we are concerned, there's no real difference between how you treat a transient CSTR versus a batch or a semi-batch reactor. Okay, there's no real special case like that. Looking at steady state conditions in CSTRs just simplifies the problems. You don't have to deal with ODEs, you can deal directly with algebraic equations. Okay, when it comes to plug flow reactors, the assumption was that everything is perfectly well mixed radially and there is no mixing in the axial direction. And that is why we can consider plug flow reactors as a batch reactor on a conveyor belt, or it can be considered as multiple CSTRs in series. Okay, and I'm just showing this slide to remind you that this is what we had considered in the first 2 weeks of this course. So go back, refer to that material, and get yourself reacquainted with some of this. Okay, thereafter we talked about stoichiometry. Okay, and this is the kind of reaction rates that you are familiar with in your undergraduate. Okay, all we had said is that we will generalize this and we will just use capital R as rate of formation of any species and small r as the rate of any particular reaction. And hopefully in your module 3 and 4 you would have seen when it comes to elementary reactions, catalytic or non-catalytic reactions, if you have for example 2H star giving H2 plus 2 star, you cannot write that as H star giving half H2, okay, because it's an elementary reaction. Elementary reaction you cannot play with stoichiometry, or you should not play with stoichiometry. I mean, there's no reason to convert an elementary reaction to non-elementary. Okay, so with that background, we had said that there is a necessity to look at a more generalized, more broader framework. Not that the earlier framework was wrong, earlier framework was a specific case of the broader framework. Earlier framework, what was the specific case? When A is -1, that is when your R, small r, is equal to minus RA. Okay, we have just generalized that situation. That's all there was to it. Okay, and then we derived the mass balance equations for well mixed reactor, and we derived the mass balance equation for a transient PFR. Okay, transient well mixed reactor, transient PFR. There are no other assumptions than the assumptions that go into well mixed reactor case over here. So you have Nk as the number of moles and not V is constant, V comes out of d by dt, none of that is there over here if you see this. Okay, and likewise this is a transient PFR. Okay, Q multiplied by Ck, you can write that as Fk also, and bottom instead of A dz it can be dV. Okay, so those are the situations. Okay, thereafter in module 1C we did some math. Okay, and the math that we used basically an integrating factor method for an equation like this. If there is no f of t, if it is just dy by dt equal to alpha y, you take y in the denominator and alpha t on the other side and you just integrate it, you get a log. Okay, we also saw the case where you had 1 divided by 1 plus k1 Ca plus k2 Ca square plus k3 Ca cube and that type of a situation. How do you integrate that? That also we had considered in module 1C. Okay, right, and and if you have dy by dt equal to alpha y to the power n, you divide by y to the power n, dy by y to the power n, you can integrate it, alpha dt you can integrate it, and that's how you can solve those cases. Okay, so most of the cases that you need to solve by hand we had covered in module 1C. The only case that we did not cover was the one that you have used for internal diffusion limitation. Okay, that was the PDE, and it wasn't necessary at that stage to cover that, but that we have we have covered it very briefly from a math perspective in module 5B. Okay, then in module, okay, these are just copy pasted slides from your module 1, 2 and so on. Okay, I have not edited them at all. These are just copy pasted, so you can go back and refer to your modules and then brush up your concepts. This is the overall species balance that We didn't exactly derive that, but we kind of went over quickly how the derivation is done, because this is not a transport phenomena class, so we didn't delve into the details of the derivation, but so this is the overall balance, and if you divide by molecular weight, this is the equation that you get. Okay, for the most part we have stuck with this equation with your Jk coming from Fick's law. Okay, so this is the situation that we have stuck with. I think there's a small change over here. Maybe I'll use black color so that it looks J hat k and Jk. Okay, J hat is basically in terms of kg per meter square second, and J is terms of moles per meter square second. Okay, so that's what this is about, and J is this. Sorry, J hat is this. Okay, so this is our Jk by Fick's law. Okay, and in 1D this is what you get. Okay, then we talked about the energy balance. Okay, and this is the sensible heat balance, which is the more usable form in chemical engineering in general. Okay, this is what you can get. Okay, so this is a very quick recap. I would suggest over the next couple of days, please go over your past lecture notes and just brush up those concepts. Those concepts, you won't remember all of them, but you would not have forgotten all of them either. Let's look at the first problem. A going to P going to Q. You have already done this for a more tougher example, that is batch reactor in module 3. Okay, this was in the context of what does partial equilibrium mean, what does pseudo steady state mean. Remember, you have already done that for batch. You are just going to do that for CSTR. It's easier to solve algebraic equations than to solve ordinary differential equations for examples like this. Okay, so yeah, A going to P going to Q for a CSTR with the equilibrium conditions, assuming that inlet contains only A with a concentration Ca in, no P, no Q. How do you solve it? I mean, if you are confident enough, literally you will be able to solve it today itself. You don't even need tomorrow's and day after tomorrow's lectures. Okay, but students who felt over the last 2 weeks that we are going a little bit too fast, start early and see whether you can solve them, and solve things together with me as we are going through with this class. Okay, if these were irreversible, then you can do the derivation, and then you will see that the irreversible case is a special case of reversible when the backward reaction is very low. Okay, third case is if the first reaction in partial equilibrium, what does it mean? And you will see what it meant for partial equilibrium in module 3 for batch reactors is exactly what it means as partial equilibrium in CSTRs. Okay, in undergraduate, if you have done partial equilibrium and pseudo steady state, you would have done dc by dt equal to 0 and all that, right? And if you remember how we did it, what we did with pseudo steady state, we said capital R is equal to 0 for pseudo steady state, and we did small r forward equal to small r backward for partial equilibrium. Okay, that is just to make our overall treatment broader. The term pseudo steady state, that has a certain genesis, but what it means for reactor level simulation, it doesn't matter whether the reactor is a batch reactor, semi batch reactor, plug flow reactor or CSTR. In all of those cases, those approximations are still valid, provided this condition is valid and this condition is valid. Okay, these are the same conditions that we dealt with in module 3. Okay, this is what you will do as the first problem. The second problem is we are going to solve a non-isothermal reactor. How we are going to do that is something that we will see in the next couple of days. Okay, again looking at some of the feedback, we will really jump into problem solving in the next class itself. Okay. Thereafter, we will talk about reactor optimization. Okay. Now, when it comes to reactor optimization, yes, what is the condition for maximizing f of x? Yes, df by dx equal to 0. Do you know where do these come from? Remember? What does df by dx mean? Slope of the tangent. Okay, so the slope of the tangent is 0. Okay, when is it a minimum? When is it a maximum? Okay, see how the slope of the tangent is varying. Look at this, as x is increasing, slope of the tangent is 1, 0 0.8, 0 0.7, 0 0.4, 0 0.2, 0 0.1, 0 0.0. What's happening? Slope is decreasing as x is increasing. Okay, slope is decreasing as x is increasing means d by dx of slope is negative. Okay, so now you have d square f by dx square is negative when you are going from left to right. Think about what happens right to left. Okay, your slope is like this, negative slope. This is -1, -0.5, -0.3, -0.2, 0. So slope is increasing as x is decreasing. Okay, so which is again negative. Okay, so if you come from both left and right, you have d square f by dx square to be less than 0 in maxima, in minima to be greater than 0, and you might have saddle. Okay, less than 0 from this side, right, greater than 0 from this side. Okay, this is especially important in, for example, multivariate case. This is single variable. There might be multiple variables. Maximize f of x comma y. Okay, at certain points it might be a maxima in x and a minima in y. That's also a possibility. So that's saddle point, right? Why is it called saddle? This represents saddle of a horse. That's the reason why it's called a saddle point, right? So imagine I'm sitting on a horse, right? The saddle is going on this side, and over here that I'm sitting, there's a backrest over here, right? So that's what a saddle point is. Okay, all of these concepts, the basic concepts, are something that we have learnt over the last 10-12 years. We are just not trained to link those concepts. Okay, when I was a student, not even when I was a student, even when I started teaching, I couldn't link those things. It's when students like you asked questions. Oh, I don't understand this. Oh, in the past this was what I was told, but what you are saying seems to be different. I'm like, okay, how is what I'm saying now different than what you have learned in your 8th standard or 9th standard? Okay, sometimes we teach you wrong things because at that age you may not really grasp the more right things. For example, there are only 3 states of matter: solid, liquid, gas. Yeah, that's a lie that we have told, because at that age, when you first heard it, we were not capable to understand anything beyond what as a child we could feel. Okay, but outside of that, those concepts are still applicable, and we are some of the times, I know it's boring sometimes and slow, but some of the times I'm trying to link those concepts. Try to explicitly look for such linkages in your master's work or your PhD work, or when you leave IIT Madras and join your job. Okay, a technician can do 70% of the things that you will be doing. That remaining 30% which adds value, you add value by connecting those things, and that's what helps career progression the most. Okay, that's my experience, and I'm sure other people's experience might be different than this. Okay, so let's go back to where we wanted to go. So why am I bringing this up? Because this is the concept that you will use in reactor optimization. Example: CB is max. Okay, what did you do? You solved the and so on, right? You solve the ODE first, then you solve this ODE. We have also done this in the beginning of this course, right? Then what did you do? You got CB and you took d by dt of that CB and equated it to 0. Or if you suddenly realize this, or if Fogler or Levenspiel realize this and you are taught by your teachers, realize this already is dc by CB by dt, you equated this to 0 and you found a time at which CA by CB is equal to K1 by K2. This is, sorry, right? So this is what you did in your undergraduate, but where did it come from? It came from this concept. Okay, what is the numerator? Let's put left and right together. What is the numerator? Okay, it is whatever you want to maximize. Okay, so that might be CB that you want to maximize, or that can be side product that you want to minimize, or it can be time that you want to minimize, anything. Okay, that's what the numerator. What comes below? What's the denominator? The variable or the parameter that you can change in order to maximize or minimize. In this case, you wanted to decide what is the time at which CB is maximum. what is the time at CB is maximum comes over here. What is the thing that you want to optimize comes over here. Put D in front of CB, numerator, put D in front of T, denominator, equate it to 0. Okay. Again, I am simplifying this, I am grossly simplifying this, but this is how you start. Once you solve 3 or 4 problems like this, you will become more expert at it and you will be able to connect multiple areas together. Okay. What if I say you find, the inlet concentration of A, let us say this is a PFR, find the inlet concentration of A such that the time is minimized to reach 10 moles of B. Okay, so you want to minimize the time d by dt, you want to find the concentration of A. So dt is in the top, dCA in the bottom. Okay, you are not actually trying to minimize that, you are trying to find time at which a particular condition is met. Okay, so your function that comes on the top will include that particular aspect. Okay, and again these are fairly complex. The last problem that I said is a fairly complex problem. This is not exactly, we won't exactly solve a problem like this, but the idea is no matter what complex situation that you are given, you should be able to break it down like this. Okay, your numerator is basically whatever your target is, your denominator is whatever your handles are. Again, and we can make it plural, your numerators are whatever your target is, your denominators are whatever are your handles, what you can change. Okay, and if it is plural, then you have to work with multivariable calculus. Multivariable calculus is what? Nothing but del. Well, del and other things, right? So instead of df by dx equal to 0, you are going to have del f equal to 0. Okay, x, y and z for example, or x and y are independent, so you will have df by dx equal to 0 and df by dy equal to 0. That gives you two equations and two unknowns, x star and y star. Okay, so that's how you can tackle all of those problems. Okay, and the last thing, and that's why I wanted the previous lectures notes to be available, and the last thing that we are going to do is to do all of this for heterogeneous reactors. Okay, and you remember how I ended my previous class talking to you about conveyor belt on which plates of food are going, and you are picking the food from conveyor belt. Okay, in this room we picked up, let's say 4 plates, next room we picked up 3 plates, next room we picked up 2 plates. Okay, so the concentration of plates along the reactor length is varying, the concentration of food along the catalyst bed or along the liquid droplet is also varying. Okay, we will come to that in the last week of this course, where these type of models could be 1D plus 1D model. These are not 2-dimensional model. This 1 dimension is inside a pellet or inside a droplet. This another dimension is inside a reactor. Okay, how to handle that, what that means and all that is something that we will do in the last week of this course. Okay, so yeah, you do not have to worry too much about that for now. Okay, so let us again recap the balance equations, right. So this is the overall mass balance equation, this is the overall energy balance equation. Okay, now if we had, and this is the derivation that we had done, if it is well mixed reactor, then you are going to have and you will have we'll just forget the T ref. Okay, so this is what we had derived for well mixed reactor systems. Okay, how did your rho Cp and all that magically come in? It didn't magically come in. It's just that in the absence of the convective term and the diffusive term, instead of that you have basically packets of fluid coming into that entire control volume and a packet of fluid going out of that control volume. Your Reynolds transport theorem that you use in order to convert your equations from ds to dv, that doesn't apply over there, and therefore you have that term remaining in the integral form. Okay, if you don't remember, that's all okay. Finally, what you need to do is basically understand or be aware of these equations. Okay, so this is what you really have. Okay, and this is what is written over here for a well mixed reactor system. Okay, please remember there is a possibility that I can make an error. Do not rely on this. As humans, we can very easily make errors, so please rely on, if for example textbook the equations are different, the textbook equations are almost definitely correct in this case. Not necessarily always. Textbook authors are also humans, they can also make mistakes, but both your textbooks have undergone multiple versions, multiple revisions, and therefore lot of errors have gotten corrected because of inputs from various people around the world. Okay, so there are a lot more errors in the first version, and as new revisions come out, lot of those errors get corrected. So if you see a discrepancy between what I have written and what is there in your textbook, go with what is there in your textbook. Okay, now when it comes to your PFR model, okay, remember what we talked about in the PFR. In PFR, you have things completely mixed in the radial direction and no mixing in the axial direction. Okay, so therefore you have dou by dou t Ck plus okay, and it's not u bar but it is just u or uz equal to 0. Okay, because it's completely mixed, so therefore concentration at the middle, concentration outside is the same, so there's no real diffusion, it's well mixed. Okay, there's no axial dispersion also, so therefore this particular term is 0. Okay, plus Rk. Okay, from this you remember we had talked about design equation. And therefore you get d by df by dv equal to r. This is the PFR equation. Okay, and if the reaction was A going to products, your R K R A, capital R A is nothing but minus R A, and therefore you put that value over there. That's how you did that, right? Okay, so this is what you got. Likewise, for temperature, you will get this is what you will get. You don't need to write it down, it's there in the very next slide. I mean, yeah, just look at it and then, yeah, whatever you need to write down in your notes so that you will remember to look the next slide, that's all you need to write, okay. But essentially this is what you have, okay. Okay. The other thing is, we have talked about rho Cp hat, okay. Rho is in terms of kg per meter cube, Cp hat is in terms of joules per kg Kelvin, C is in terms of moles per meter cube, Cpk is in terms of joules per mole Kelvin. Okay. So, Cp hat, these are the units, Cp, small cp, these are the units, left hand side, right hand side, okay. So, these are equivalent, okay. Because of this, you can very well write this okay, both are same, and depending on the data that is given to you, you may have to use one or the other. Okay. Volumetric flow rate multiplied by Ck. Okay. Another thing that you might be able to use is mole fraction ideal gas Z equal to 1. Okay. So, P K equal to CKRT. Okay. All of these concepts you have used, if you are undergraduate in chemical engineering, you have used them in volume expansion, etc. For gas phase, there is no volume expansion business for liquid phase. What that means, how we are going to use that, all of that next class. Okay. Next class, instead of talking about theory and going over rest of these lecture notes, we will solve a problem. Okay. Now, for batch reactor, and again in the next 3 minutes, 4 minutes, I will quickly go over what our plan is going to be next. Batch reactor, what do you have? You start with this equation, batch means this is not here, this is not valid, so you have d Nk by dt equal to Rkv. dNK by dt equal to RKV. Energy balance V rho Cp dt by dt equal to the reaction heat term. Okay. Isochoric is volume is constant, isobaric pressure is constant. This is for gas phase, and you have solved a problem in assignment 1, you have solved an example in your midterm, and most of you got the midterm question correct, right? At least that part of it. Okay. Equilibrium, remember, full marks if you get G and KEQ. If you use KEQ equal to 1, then 3-mark problem. That was the problem from your assignment, from your quiz, if you remember. Okay, that's the one that I'm talking about. So you have done this before for gas phase systems. Okay, just that we are going to do it once again. Okay, so if you have an equation like this, rate of reaction can be as complex as it needs to. That's not a problem. You can do it using a conversion based approach, or you can do it using a concentration based approach. If you remember in your undergraduate, if you had reaction A going to B, you had to design a reactor, you use dx by dt. But if it was A going to B going to C, where you wanted to maximize Cb, you didn't use dx by dt, instead you use dc by dt. Okay, they are both equivalent if you know what to do, as well as one more equivalent method is based on extent of reaction. All of those are equivalent as long as you don't make any mistakes. Okay, so you can, of course, you can ask me those questions, but this I'm just preempting the question. Oh, in this book or over here or so on and so forth, solve this problem using this, I solved this problem using this, in the classes you have solved it using this. Whatever you are comfortable, you can absolutely use it, not a problem, absolutely. Okay, and this slide basically shows this method and this method is exactly equivalent. You will get the exact same result from both. Okay. For non-isothermal system, you also need to solve this, and when you solve using non-isothermal system, this is again process calculation type of an approach. This is basically your delta T adiabatic, T equal to T naught plus delta T adiabatic multiplied by conversion, or likewise you can use this. What are you doing? You have two equations in two unknowns, concentration and temperature. You are converting the temperature equation and expressing it in concentration and plugging it into the previous equation. That is what you are doing. How to do it? Next to next lecture. Okay. CSTR, same concept, but you have the transient term as 0, you have inlet, outlet, reaction. Because you do not have any d by dt term, any d by d term, therefore it is algebraic equations. So you now have algebraic equations. Happily enough, the only non-linear term comes in because of reaction term. Because of inlet and outlet, they are still linear terms. So that's a good thing, because linear is easier to solve, or linear terms are easier to handle. Okay. And what if you have complex reactions? Same concept, you apply one by one to each of those species, and you will be able to solve as complex a reaction as network as you want. Okay. What if it is non-isothermal? Same concept, and you will see that your temperature balance essentially turns out to be similar to your batch reactor. You have T equal to T naught plus delta T adiabatic multiplied by conversion, and if there is any heat transfer term, that heat transfer term will also get added. Okay, this is the adiabatic temperature rise. Okay, we will take up a problem and try to solve it in the class. And then finally plug flow reactor, again same idea, dF by dV equal to reaction rate and dt by dV equal to, okay, mCp is nothing but Q rho Cp. Okay, so that's the term that comes in. If there is pressure drop is significant in gas phase, then you also have to consider pressure drop. Liquid phase, pressure drops can be significant, but they don't feature into your reactions. We are going to take in the last week of this course and the last problem of your assignment 5, we are going to connect what you did in particle size with in module 5b. Large particle, mass transfer limitation, small particle, no mass transfer limitation. Large particle, pressure drop in the reactor is low, small particle, pressure drop in the reactor is high. Okay, so there is a trade-off. That trade-off we are going to consider in an example that you will solve towards the end of this. Okay, so that's going to be our game plan for. So we have 3 weeks left, 11 lectures left. Try to cover it in, as probably 3 lectures, 6 tutorials, or 3 lectures, 5 tutorials, something like that. Okay, not so it will be solved tutorials, not where you are necessarily going to solve it. Maybe 2 tutorials is where you will solve, but essentially just trying to see that we can bring in more problem solving, like what you requested in your feedback. Okay. All right. Any questions? Okay.